Thank you for joining us. So the topic, as you see, is rapid calculation of residual stresses in part scale additive manufacturing. But before we start, I would just like to share with you that I am from Mumbai and I came just 4 days back and still going through some, hangover. So some kind of residual stresses are also with me now. But that's not what we are talking of. We are talking of residual stresses in additive manufacturing. So as we see here, the laser powder bed fusion as one of the prime processes in additive manufacturing that uses metal powders in a layer by layer, track by track manner and deposit and build a three-dimensional part. And it prints three-dimensional parts which are of complex features, very complex features, as we can see here, which on one side is really an achievement. But at the same time, if we see on this side, as it builds complex features, parts like this from bottom to top in a layer by layer manner, it also goes through a very high temperature gradient. And this temperature gradient is a real problem. One of the most important problems because of this temperature gradient is residual stresses. And that leads to, as you can see, it can lead to separation of supports from the part. It can lead to crack in the part because of the stresses which have not been perhaps designed earlier or which have not been thought of. It would emerge like this, such kind of cracks that would make the part completely unsuitable. It can lead to crash of blades, for example, which we have just seen in the previous picture. It can also lead to delamination of part from the base plate. So there can be so many such problems that can happen because of the residual stresses that come or that evolve because of the temperature gradient. And of course, the expansion and contraction out of that. So a question arises that as the process says, it's a very complex process. It starts with metal powder. It prepares a part three-dimensional in a very complex manner. And end of the day, if we see these cracks that happen at the final stage, it's really a huge wastage of money, huge wastage of time, resource. So one way is, of course, to see how we can sort of appreciate or predict or estimate what is going to be the residual stresses because of certain application of the variables and the process. As we know, numerical modeling of residual stresses like finite element method-based model, these have been very, very regular, and we have learned such models. They are very nice, and they have been very successful to calculate thermomechanical residual stresses in case of welding. So there have been previous knowledge on that. However, when such methods are being applied to additive manufacturing, like laser powder bed fusion, where the parts are built, as you have seen, layer by layer, track by track manner, it can lead to, a large problem. Like it can have well over 1,000 layers. Each layer can be designed or modeled by more than 1,000,000 elements. Each nodes within the elements, as you know, in the finite element method, they can have 4 degrees of freedom, like 3 different displacements, temperature. And if we want to design the whole process, that means you can think of a three-dimensional part having multiple tracks, thousands of layers, many tracks. It can lead to a severe or a huge amount of problem, or a huge problem. Here is an estimate of what has been already noticed. Like if we are thinking of typically modeling a 3-layer stuff, 3-layer deposit of simple, this kind of cross-section, it is already noticed that it can take something around 92 hours just for one task, just for one simulation. And imagine that this is perhaps done only for a one process condition. Now you try to see the process condition, this is more. And more importantly, as you see, as we increase the number of layers, that means the part size is increasing, the total time is increasing almost in an exponential manner, 30 layers. I mean, almost nothing, 1.5 millimeter height of 30 layer. I mean, just a little bit of stuff, nothing compared to a real part that itself can ask for something around 7,000 hours to just get a simple idea of residual stress distribution. Again, for a particular process condition. So we can imagine how difficult it is to get some immediate answer of what is going to happen, what will be the real, I mean, what would be the most optimized set of parameters. But still, this is so far the only possible ways now, because the other alternative is just go and try to do some process and try to make some part, it may get cracked. That's a very costly alternative. So the question is, can we do something that will not give us this kind of torturous situation? So one alternate possibility is to try to see where it is emerging from, how the residual stress is actually happening. If we look at a simple situation, how it is happening, a typical base plate on which we are depositing layers. So let us imagine this, a base plate, we can think of as a kind of section of multiple just strips, okay? As we go up, it's getting hotter because it's more and more near to the deposited layer that's coming because of the molten powders and so on. So as we deposit one layer and this molten, so it will expand, it will create an expansion. So the base plate would tend to sort of deform in this manner. So during heating, we will have some kind of compressive stress followed by tensile stress, and kind of equilibrium will happen through the thickness of this combination assembly. As this will now solidify, this will try to shrink, and this will be sort of reacting. Some reaction stress will automatically develop against the shrinkage. So tensile stress will start evolving towards the top, and this will be slowly equilibrated through the thickness, and a new stress distribution will evolve. It cools down to room temperature, the tensile stress increases further, and furthermore, this distribution evolves. So imagine a situation, if this is the distribution of stresses that happens for the deposition of one layer on a typical substrate, perhaps it's not so bad if we just think it. It's a little simple, little bit of constant through the thin layer. Now remember, in laser powder bed fusion, the layer thickness is not really so great. So perhaps we can think of this constant, a linear variation from here to here to a maximum compressive point, and then going further down to the tensile state as it will be equilibrated. Now the question is, this evolution needs to be captured in a manner that comes out of a mechanistic relation, equilibrium of forces, equilibrium of moments because of expansion and contraction. So what's next? Let us look at how can we do this using simple mechanistic relations. So we have simple mechanistic relation like equilibrium of force. So stress multiplied by area is equal to force. Overall force will be in equilibrium. Likewise, overall moment will be in equilibrium. Okay. And with simple assumptions like we are thinking of linear elastic properties with material with constant properties, no boundary effect, no complexity on the boundary side. And we are considering, because it is sort of depositing layers on the track, so longitudinal stress is more important. And this we have also learned in welding. So our previous learning is helping us. So other stresses we are considering, they are smaller, longitudinal stress is dominant. So if it is only single layer, it will evolve in this manner. Now this is fine, but this is only the beginning of the show. There will be multiple layers. How it will evolve? Let us see. So we have deposited one layer, stress generated, it is equilibrated. Second layer comes, new stress generated, it is now getting evolved. Another layer deposited, it is again new stress coming, and then it is getting evolved. Another layer, it's getting new stress, it's getting. So basically, this is the thing we have to somehow capture. We have to capture in a manner so that it is fast enough and it can compete with the numerical model, and it can be done rapidly, accurately. Okay, so each layer, when it is deposited, comes with a baggage that it has a peak tensile residual stress. And because of the equilibrium, whatever was there earlier, because of the previous layer deposition, they will be slowly getting redistributed. Okay, now this is what will come. If we look at that, this is something we are kind of visualizing. So whatever be the number of layers, as it will go up, imagine that n number of layers are being deposited one after the other. As it will go up, slowly there would be a redistribution through the thickness of the layer and the base plate, and this slope will continue to get redistributed, try to do some kind of redistribution among themselves, and the total amount of stress, how much it will come towards the bottom of the base plate, will depend on how many layers we are depositing. So basically, it's a balancing of stresses. That's all we have to capture. We need the information, but that what is the stress a layer is bringing in when it is coming in. Okay, so the idea is, can we get this also faster from some way, in some way? Okay, so what we have done now, don't go for any numerical model. We have already so much of data available. People have done experiments. We look at the basic causative situations. Who are those variables that is creating those issues? Okay, so imagine we have done a scaling analysis, typical dimensionless pi analysis by using pi theorem. Try to do all important variables in a dimensionless manner. So the peak residual stress coming with every layer, we non-dimensionalize it by dividing it with the corresponding yield stress of the material, room temperature yield stress of the material. Heat input per unit build volume. So larger the amount of heat, more amount would be the melting, more will be the stresses because of contraction. Okay, so non-dimensionalize it by dividing it with the corresponding enthalpy. So larger this ratio, more amount of heat is evolved, more amount of melting is happening, more residual stress will come. Beta into delta T. Larger the beta for a material, it will create a larger amount of strain, larger stresses. It is already non-dimensional. We don't have to, we are so saved on that. No ratio is required. Preheat temperature. Larger the preheat temperature means sometimes it is done already. By experience, we are bringing in the science into it. We don't have to do anything further. Okay, larger the preheat temperature, lesser would be the thermal strain. So higher the preheat temperature, reduced would be the thermal strain and stress. Again, how should we non-dimensionalize it? Just divide it with the ambient temperature. So once again, higher the ratio, higher is the stress. Lower is the residual stress. Track length, we again know this very well from welding. Longer you go without stopping, more you are building the stresses. So larger the track length, higher would be the stresses. And again, we need to non-dimensionalize it, divide it by the laser spot radius. So kind of do a non-dimensional parameter. And higher the thermal diffusivity of an element, more uniform the temperature. Lesser would be the thermal gradient. Lesser would be the strain, lesser would be the stresses. So we get an understanding that these are the key variables which will influence internally to get this evolution of the residual stress. And while variable like heat input per unit build volume, thermal strain, larger track length, they will directly impact the residual stress. Variables like preheat temperature, thermal diffusivity, they will try to save it. They will try to reduce the stresses. So throw in all the data that we have from the literature and don't be very miser only with one material. Don't try to save your situation. Try to see what is the destructive situation. Dump in all material, all the experiments from whatever you have. And then try to see fit a relation. All we know that some of them will go to the numerator, some would be on the denominator because of their positive relation, and try to fit a relation between the peak residual stress and these variables. This we have found, and we have seen a relation can be obtained with a fair R-square, fair correlation coefficient. Of course, it took some time. It's okay. So once we did it, once we got this, then it is very easy. Now we have our analytical approach. We have
They said business casual, so
what will be the
whatever that is.
what will be the peak residual stress for every new layer? It comes in, and then it would be distributed through the thickness by an iterative calculation. It is being done from the layer to the through the thickness. So as we can see here, this is done. This is the
So Dr. Kubi is gonna be thinking, oh, last year I attended this seminar and I wasn't even
through
there.
the thickness along this dashed line.
Yeah, I think it's just better I leave.
Calculation, not very far. Yes, it is far, but not very far. Okay, that's the good point about it. Go for further. 2000 layers. Okay, 2000 layer deposition of IN718 powder alloy. We use the relation, get for every layer as it is getting deposited the residual stress. Every new layer comes with the residual stress, and whatever was there earlier, it is getting redistributed. So the final residual stress distribution through the thickness analytically estimated is something like this. And we are so happy to see that we are more closer to the experimentally measured values represented by this green, and compared to the numerically computed results. Again, this is from independent literature. We go for more complex situations. These are only simple walls. We go for more complex situations, like a build with not only multiple layers, but also with an irregular cross section. Okay, we tried. And this can be compensated by doing some kind of stiffness, okay, adjustment, because it's the area is less, its stiffness would be less. This can be incorporated in the model. This is already there because we are doing a moment equilibrium. So it will automatically go inside. And there also, as you can see, this analytically computed stress distribution through this, represented by this blue line, through the thickness along this section, are not very far from the experimentally measured results by contour method and the numerically computed results. Remember this now. Now you see, this is very difficult. Numerical model could not really do much. It only finished here, but we have no problem. It can do all through this from top to bottom. And this is not sufficient, because this is not the only goal to do this. The goal is here. This is the most important goal. If we see a typical computed layer with so many nodes and elements, with a, desktop or something closer to, a better computational machine, if we can think of, it takes nearly 8.4 hours. Analytical model takes this much of time because it is doing only a simple Excel-based calculation, nothing else. It's already there. It's just compensating, just equilibrating the calculation, forces and moment. A 200 layer, it takes around 1600 hours. It takes 0.25 hours. Okay, and this is how the time comes in. Okay, and this can go further. We have already done now many more layers, and we have to see how far, how good those results are coming. But this is what we can show, that how fast it can do. Not only this, look at this scaling analysis we have done, which is an engine to this analytically calculated analytical approach. These results can also be plotted in terms of map. Like, imagine this is y by sigma y, that is yield stress, as if, the ratio of yield stress to material, peak residual stress to yield stress. So larger this value, that means that peak residual stress is closer to the material yield stress, which is bad. If you look at this map of peak tensile residual stress to material yield stress ratio as a function of power to speed for 4 different materials, okay, one thing very quickly you can imagine, you can get out of it. Just look at that for the same X and Y scale, okay, for the same X and Y scale, where the lines are more distributed, here the lines are more distributed, which means only this much of high residual stress will be happening. 0.8 times sigma y would be the residual stress for aluminum alloy. only at so much of high power. Whereas this can happen in titanium alloy somewhere around 200 watt. What does that mean? This simply tells us, look, aluminum is a more, tolerant material. If you do something with aluminum, chances are you may get other defects, no problem. We don't know, but at least for residual stress, it will give you some kind of more tolerant situation. But if you are building with a titanium alloy, be very, very careful, because you would get very high residual stress at a much lower power, and it can lead to crack. It also shows, which of course we know is not very difficult, that if you increase power, your stress will increase. If you increase speed, your stress will reduce. This anyway you will know, because that is directly connected to the heat input, but unit length of deposition that we are doing. Okay, so what we are presenting now, what we have I have tried to present you is, this is an approach which can do something exclusively that cannot be done today by any other model, which is it can predict, it can calculate the residual stress distribution through the deposition of layers, as many layers as you can think of, simply by a laptop computer, as fast as you can imagine. We don't need an FEM model, and perhaps we don't even think of that because they have a limitation. If there are something around 2000 or 3000 layers, numerical model is always difficult. Okay, so this is an exclusive method which is showed here, that can calculate rapid and accurate residual stresses in part scale, which is of importance today. It can do so nearly 1000 times faster than numerical models, maybe more if we can also do some perfection in our calculation, perhaps slowly as we are working further on that. And the necessary peak stress that is to be given as an input to the calculation, which comes from scaling analysis, can be used for process maps readily for making design calculations or designing AM variables to select which parameters you must choose to mitigate stresses, which powder you must choose if you have a choice to mitigate residual stresses. Thank you very much.